Alright friends, welcome back. In this video I'd like to go ahead and take that second day for section 1.2, and we're going to continue to talk about equations in this video in one variable, and we're also going to take a look at a different method for finding intercepts. Okay, so in the last video we showed you how to find intercepts graphically by using the calculator. In this video what I'd like you to do is to study this method of finding your intercepts algebraically. Okay, it's always good to have multiple different methods for doing the same thing, because where one method may be annoying or would fail, another method could pick up the slack, right? So finding algebraically your intercepts. Well, don't forget what an intercept is. So when you have a graph, like in this case, say this linear function right here, there would be a place where you would cross the x-axis, and there would be a place that you would cross the y-axis. And every function is different, so maybe you would have a function that doesn't cross the x or doesn't cross the y. But in the case wherever you cross the x and y-axis, you would have this point with these coordinates, okay? And it's these coordinates that are going to kind of help us make sense of the algebraic method here, because whenever you look at your x-intercept, that is that's a point with coordinates x, which means however far to the right you went, or however far to the left you went, of course. But then the y would, of course, be 0. And that is signifying that if I want to stay on the x-axis, I'm not going to go up or down any. I'm going to stay on the x-axis, and that y-coordinate would be 0. Similarly, since to get to the y-intercept, your x-coordinate would be 0, because you're not going to go to the left or to the right any. You're going to stay on the y-axis. So that is why algebraically, whenever you try to find your intercepts, you are going to go ahead and set y equal to 0 and solve for x in the case you're trying to find your x-intercept. And then in the case you find your y-intercept, you would go ahead and do a similar process, but you're going to set yourself up to solve for your y. So in other words, you're going to go ahead and set x equal to 0 and solve for y, okay? And we are going to go ahead and make sure that we put our points in these forms here, because these are coordinate points that we would graph and see those coordinates there. So I've already gotten us a little bit of a head start. So in the case of this first example here, we have this equation y is equal to 12 minus 5x. In these cases, we would just want to go ahead and solve for these intercepts individually. So again, for the x-intercept, we're going to go ahead and set your y equal to 0 and then solve for x, right? So let's get that y out of there. Let's go ahead and replace that with a 0. Over here on this other equation, let's go ahead and get this x out of here, and we're going to go ahead and replace that with a 0, which I might just go ahead and simply do in parentheses. And then we're just going to go ahead and solve for the other variable here. So in the case of this equation here on the right, I might just go ahead and add 5x to both sides just to avoid having to deal with a negative. I'd end up here with 5x is equal to 12, and then of course divide both sides by 5. And we would see here that x just turns out to be a fraction here, which is fine. That is going to be 12 divided by 5. Or as a point with coordinates, that would simply just give us 12 over 5 as the x-coordinate, and then 0 as the y-coordinate. Okay, so that would be our x-intercept for this equation. For the y-intercept, very, very simply here, 5 times 0 would just make 0. And then 0 minus 12 would just simply make a 12. And so that would correspond to a point with coordinates 0, 12, and that would be your y-intercept. Moving on here to this next example, same thing. We're just going to go ahead and plug in 0 for y and then solve for x in the case of the x-intercept, plug in 0 for x and then solve for y in the case of the y-intercept. Well, I want you to notice here, right? If I were to plug in 0 for a variable, in that right equation, that would be 3 times 0, or in other words, that would just be 0. And what that means is that this whole term falls out of the equation. So what I'm going to do from now on is just go ahead and erase the term with the y in it if I'm plugging in 0 for y. And same thing on the other equation if I'm plugging in 0 for x, right? If I plug in 0 for x here, that's 2 times 0, and that just makes 0. And then that whole term disappears right there. So what I'm going to do is I'm just going to go ahead and erase those terms if I'm plugging in a 0, and then I'm going to go ahead and solve for what's remaining here. So in other words, I would just simply divide both sides by 2 in this first equation and get x is equal to 5. And in this other equation, I would simply just go ahead and divide both sides by positive 3 and then get a fraction there as my result there. So that would be 10 over 3. And then just don't forget that these correspond to point coordinates, so that would be 5, 0, and then 0, 10 over 3. In this next example here, we have this following equation right here. So even though this looks like an equation where y is not solved for, and it looks like we could do some work to simplify it, we don't have to. Again, we're going to stick with that same general strategy of if I plug in 0 for y, it means that the y term is going to disappear. If I plug in 0 for x, it means that that x term is going to disappear. And so I end up with these equations respectively. I can just go ahead and use my inverse operations to solve those real quick. So let me just go ahead and perform that on all sides of both equations here. So that's going to leave me with 2x over 5 is equal to negative 8 in that first equation. And then in the second equation, I end up with negative 3y is equal to negative 8. And then if I go through and solve these, a fancy trick that you could do on that one on the left is that since you just have 2 over 5, you can multiply everything by a 5 over 2, and that would get the x by itself there. And so that would leave over on this other side, that would be negative 20 if you took 5 over 2 and multiplied times negative 8. Over here on the equation on the right-hand side, if I just go ahead and simply divide both sides by negative 3, I would end up with a negative divided by a negative, which of course makes a positive, and that would be a fraction 8 over 3. And then just don't forget that these would be coordinate points, so this would be negative 20, 0, and this would be 0, 8 over 3. In the case of this last one, I got this equation here. It looks like I got some decimal values in it, but it doesn't mean that anything changes. If I'm trying to find my x-intercept, I'm going to go ahead and plug in 0 for y, which means that my y term disappears. And if I am trying to find my y-intercept, that means I'm going to go ahead and plug in 0 for x, and that means that my x term is going to disappear on me. As soon as my note-taking program feels like it wants to erase, there it goes, okay? And now what that's going to mean is that I've got these equations going on now, and I tried to select that, but that didn't really work out, so let me go ahead and erase that and write that a little bit closer over there. There we go. Let's go ahead and solve these, right? So I would go ahead and subtract 1.2 from both sides, and that would give me 0.75 x is equal to negative 1.2. Over here on this side, I'm going to go ahead and do the same thing. So subtract 1.2 from both sides. It's going to give me 4y is equal to negative 1.2. And then go ahead and divide both sides again. This is just the same general steps as we've always seen in all of these different equations here. Just going through it, right? So it doesn't mean anything changes, especially when we have our decimals here. Doesn't mean that anything at all changes here. We're just going to have the following. So I'm going to go ahead and take my calculator real quick and get these solved for here real quick. So when you take negative 1.2 and divide it by negative 1.75, you are going to get positive 1.6. And then on the other one, if you take negative 1.2 and divide it by 4, you are going to get negative 0.3. So just don't forget these corresponding coordinate points. So that would be 1.60 and then 0, negative 1.3. So to find your intercepts algebraically, it's super, super easy to do. You would just plug in 0 for one of your variables and then solve for the one that you want. In each one of these cases, again, these are the places on the graph where these equations would cross the x and the y axes, respectively. In this next little section, we're going to go through solving some other different types of equations, and I just don't want you to forget that when you solve types of equations, there are the ones that have one solution, like the ones that you're looking at here. In the case of number 13, I end up with x is equal to 4. In the case of number 14, I end up with x is equal to 5. You could end up with equations like that just have one solution, or you could end up with equations that have no real solution or all real solutions. Okay, so just to kind of take a look at some of those types of equations, here's another one where we would simply just have one final answer at the very end of the problem. Ones where we have to do distributive property first, combine like terms, collect all of our terms to one side so we get x isolated. But we also have ones that don't have any solutions here, right? So these ones lead to contradictions. So we would do all the usual steps, but then we would end up with this contradiction that says negative 9 is equal to 8, which of course is not true. And so we would conclude there that we don't have any real solution, okay? Well, what I want to do for the rest of this video is take you through a couple of different equations, then remind you of some of the more sophisticated problem-solving strategies that we have in our toolbox, right? So, for example, let's say you're looking at number 19 here. 19 is unique in that it's got some rational expressions in it, which is something that we took a previous video to discuss, but just remember that these rational expressions, these have denominators, and whenever you're working with denominators, it gets a little bit tricky to work with algebraically unless you remember some of the tools that are in our toolbox here. So because we have some divided by x plus 4s, for that reason, what I'm going to do for this equation first is I'm going to multiply the entire equation times x plus 4. And I'm specifically doing that because times x plus 4 and divided by x plus 4, those are inverse operations and they would just simply cancel each other out. So that means when I go through and distribute this to everything in the equation, since I'm multiplying the entire equation by it, what that's going to mean is that these divided by x plus 4s are going to cancel with this times x plus 4 that I'm distributing into it. And then that would simply just leave me with x plus 4. And then I've got my plus 2 times x plus 4. And then I've got my equals 0 times x plus 4. Well, we know on the right-hand side that 0 times x plus 4 would just simply be 0, so I'm not even going to write it that way. And then for the rest of the equation, you can just go ahead and solve this in the usual way, where you're just going to go ahead and go through, and you're going to distribute in that positive 2. Okay, so we're going to have x plus 4 plus 2x plus 8 is equal to 0. and then just go ahead and combine some like terms and continue to solve. So you've got some like terms there. You're going to end up 3x plus 12 is equal to 0. Subtract 12 from both sides. 3x is equal to negative 12. And then divide both sides by 3. You would get x is equal to negative 4. Okay? Now, I wanted to take you through this because it does look like we end up with a single solution here, but remember that we have that way in the calculator of being able to check this solution. So remember in the last video we discussed that process. And if you were to check it here, remember in the calculator you would go ahead and store negative 4 into x, and then you would type in the left-hand side and see if it gave you what was on the right-hand side. If you try to do that here, it's going to say error, because what that's going to mean is you tried to take this negative 4 and plug it in for x in the denominator, but that would be negative 4 plus 4, which would make 0 in the denominator. And we never want to have 0 in the denominator, so that's why it gave us the error. What this means is that we're going to start to throw equations your way that you're going to solve and get an answer for in the same general problem-solving process that you guys are always used to, but whenever we check it, we're going to have to throw it out. This is something we give a name to in math, and this is something called an extraneous solution. And again, the definition of that is just simply it's a solution that we get by the natural problem-solving process, but whenever we try to plug it back into our equation, we don't get a right answer, right? We have something that is not true. So our conclusion on this properly would be to say that this equation does not have any real solutions. In number 21 here, just to take you through this real quick, just don't forget that sometimes you are going to need to factor what you are given, right? So if you notice any of those classic factoring formulas from back in the day, then they would definitely need to apply. Like in this case, the difference of two squares we would factor into x plus 3 times x minus 3. And if you do that, this might be something where you can go ahead and signify that I'm going to multiply everything by a copy of x plus 3, because I got some x plus 3's in the denominator, and also a copy of x minus 3, since I have x minus 3's in the denominator. And just to remind you how this works, we took a video in the past to talk about this, but if we distribute that to absolutely everything, 1, 2, 3, then what's going to happen is that this whole denominator is going to cancel with the one that we had there, so that's just going to leave us with a 10 on the right-hand side. And then as we continue to distribute these into the other terms on the left-hand side, this x minus 3 would cancel with the x minus 3 that we distributed to it, just leaving us with simply 1 times the extra copy of x plus 3 that we had remaining there. So I'll write that. I'll say 1 times x plus 3. And then this would cancel out here with the copy of x plus 3 out here, and just leave us with the 1 times x minus 3. So 1 times x minus 3 is what we would have left over there. When we distribute in those ones, it's not going to change anything, so I'm just going to get rid of these ones in these parentheses. Combine some like terms there. I'm going to have 2x plus 0, or in other words, just 2x is equal to 10, and that means, of course, that x would be equal to 5. So we end up with this answer after we get through our problem-solving process, but again, if you go to the calculator and check, just like we talked about in the last video, it always is something that you need to check to make sure is an actual solution. And here it turns out that, yes, this is an actual solution. This doesn't create any problems for us by creating 0 in a denominator. You definitely see that what you get on the left-hand side is the exact same as what you get on the right-hand side. And so since those match up, this will be a legit solution for us. So just making sure that we are always checking our solutions before we call the problem finished. The last example that I want to take care of here in this video is an example where you have an equation where you have two different variables. You notice you have x, which is the thing we need to solve for according to the directions, but you also have this variable a, and we need to just kind of be aware of how you would deal with that. Well, we're going to go ahead and deal with this in the exact same way that you guys have always dealt with equations, which is to collect everything with an x in it on one side and collect everything without an x in it on the other side. So I'll say that here. X's need to be collected to one side and leave everything else on the other side. So as a first step here, I might just go ahead and go through, and I notice here that I've got some distributed property going on, so I'll go ahead and distribute a 4 inside and call that 4x plus 8 minus ax is equal to x plus 5. And then everything with an x in it, I just need to make sure I collect to one side. So here I've got a 4x, I've got a minus ax, and I've got an x on the right-hand side. So since I have more things with an x in it on the left than I do on the right, I'm just going to go ahead and move this x over to the right-hand side, in which case I would have 3x plus 8 minus ax is equal to positive 5. And then everything without an x next to it, I'm going to go ahead and move it to the other side. So I'm going to move this 8 over, and then that gives me, of course, actually that's not an 8, is it? That's supposed to be a 4. So let me go ahead and change that. I think I was thinking before that I was distributing in something to a 2 there. So let me go ahead and fix that real quick. You guys are probably confused about that. I apologize. So yeah, let's go ahead and change that to a 4. So subtract 4 from both sides, and we would end up here with 3x minus ax is equal to 5 minus 4, which makes 1. Now, why does that help? Well, because everything now that has an x in it is on one side of the equation. And what I can do is I can treat that x as a GCF that I can factor out of all the terms that had an x in it from before. And so what does that leave behind? That leaves behind 3 minus a. Okay? Now, our last step of this, since this is x times that number, 3 minus a, our last step of this would be to go ahead and divide that out. Okay, so divide out 3 minus a from both sides. And typically in algebra, this is something that's pretty frowned upon, actually, because you don't really know what the value of 3 minus a is. For all we know, playing the role of a could be 3, and 3 minus 3 would make 0, which means that I'm dividing by 0 on both sides. So that's typically something that you find a lot of mathematicians are pretty uncomfortable with, but it is something that we are allowed to do as long as we just tell our reader that playing the role of a is not allowed to be positive 3, okay? Meaning that what we just did in that last step is a legal move as long as we say to the reader that a is not allowed to be equal to 3, okay? And so if you have two different variables in the same equation, that's still something that we're able to handle. It's just one of those things we're going to have to tack a note on at the very end, okay? So I hope this video has been of some help to you. Please let me know if you guys have any questions whatsoever. I'm always happy to answer whatever questions you have. Thank you so much for your attention, and I will speak to you guys in the next one.